Okay, on this slide we have our basic trigonometric identities, which ultimately are just the relationships, the reciprocal relationships between cosine and secant, cosecant, sine, cotangent, tangent. They can be written in terms of either one of the any one of the six. Okay, and then also what we've been working with quite a bit in our previous chapter was the fact that the definition of tangent is sine over cosine, cotangent is cosine over sine. Okay, so these are our basic trigonometric identities. Okay, we can use these anytime we so choose, as we'll see in a minute. Like for instance, if I wanted to do something with cosecant, I could at any time I want to, I could replace it with 1 over sine, because those two things are equal to each other. So, like I said, these are ones that we already know, so we'll be using them quite often. Okay, Austin? Yes, it is. Thank you. Notice that. Yes, that is a typo. Should be sine on the bottom. There we go. So cosine over sine. Yeah, that would be pretty crazy if we changed it now, wouldn't it? Okay. So going forward from there, like I said, we're going to use these quite often. Okay. And we're going to also use what we call the Pythagorean identities quite often as well. Okay. So I want to spend a few minutes looking at these identities and discuss why they are identities and why they're true. So we'll start out with this first one. Okay. It says that if I have cosine squared of theta plus sine squared of theta, that equals 1. Okay, so I want to illustrate a couple things for that one. First of all, why? Well, remember when we have the unit circle, okay, the unit circle is a circle with a center at 0, 0 and a radius of 1. Okay, and every point on the unit circle has coordinates, cosine t, sine t. And keep in mind the t represents the angle, so it could be t, it could be theta, it could be x, could be whatever letter we choose. Fair enough? Okay. So with that said, if I look at the triangle that's created by choosing a point on the unit circle, it's always going to be a right triangle. And it's always going to have one leg cosine, one leg sine. Okay. And hypotenuse is always going to equal what? 1. Okay. Because this is a circle that has a radius of 1, no matter what point we choose. So therefore, just by the Pythagorean theorem, couldn't I take the sine of t squared plus the cosine of t squared and have it equal 1? That should be true every time, shouldn't it? Okay. Now I want to caution you on the notation here just to make sure we're clear. Okay, when I take the sine of t, that's going to be now a value, because t is an angle. When I take the sine of it, it's going to be a value, and then I'm going to square it last. Okay. That means the same thing as what we have right up here. Okay, when I write sine of t all squared, that means the same as sine squared t. Okay, so we're not squaring the word sine here because that wouldn't make any sense. Okay, what we're doing is we're taking sine of t, getting an answer, and we're squaring it. So you need to recognize that these two notations are the same. So when you see that notation, you need to recognize that if I were to have to do that with my calculator, like for instance, if I asked you to do the sine squared of, let's say, pi over 6. Okay, if I told you to do sine squared of pi over 6, okay, sequence-wise, we would find the sine of pi over 6 first, and then we would square it last. Okay, so keep in mind that's what that notation means. So I would go sine of pi over 6, that's going to be a half, and then I would square it, and my final answer then would be a quarter. So what is the sine squared of pi over 6? It's a quarter, because the sine of pi over 6 is 1/2. If I square it after that, I get a quarter. Now, I also want to illustrate that this is true, looking at the unit circle again. If I were to pick a point on the unit circle, like let's say pi over 6, we know it has coordinates radical 3 over 2, 1/2. True? And so based on our work that we just did here, if I were to use the Pythagorean theorem and square both of those, what had I better get? It better equal 1, shouldn't it? So no matter what point I pick on the unit circle, if I square this one, I'm going to get 3 on top, 4 on the bottom. This one's going to be 1 on top, 4 on the bottom. And what does 3/4 plus 1/4 equal? 1. Okay, so no matter what point I pick on the unit circle, okay, it should make this sentence right here true, shouldn't it? Okay, because I'm going to square whatever coordinates I have for cosine and sine. If I square them, it had better equal 1, okay, if they are on the unit circle. Fair enough? Now, we might ask then, well, how in the world did they get this sentence? 1 plus tangent squared equals secant squared. Okay? Because we don't really know anything about relationships between tangents and secants on the unit circle, do we? Okay, so here's how they got that. They started out with the fact that the cosine squared plus the sine squared equals 1, okay, which is a true sentence. Okay, and then what they did next is they used the multiplication property of equality, and they took that identity, which we know is already true, and they multiplied it by 1 over cosine squared theta. Okay. All right, and remember, with when we have an equality, it's okay to multiply the entire equation by something and still have an equality. That's the multiplication property of equality that we learned about in algebra. So let's see what would happen if we did that. We'd have cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta equals 1 over cosine squared theta. Okay. And ultimately, what is this? 1. And if I have sine squared theta over cosine squared theta, that's really what? That's tangent squared theta. And what's 1 over cosine theta? Secant. So therefore, 1 over cosine squared would be just simply secant squared. All right. So one question would be, do you have to memorize this particular identity? No, because you can always do what I just did and get it again, couldn't you? So if you forget, you can start with this one. This one I would have memorized, and you should already anyway, because it's essentially how the unit circle operates, right? Okay. So, but after that, you can memorize this if you want to, but you don't need to, because you can always just re-find it just like I did just now. Okay. Similarly, if I were to do the same thing with cosine squared theta plus sine squared theta equals 1, and I multiply the whole thing by 1 over sine squared theta, okay, I'm going to wind up with cosine squared theta over sine squared theta plus sine squared theta over sine squared theta, and over 1 over sine squared theta equals. And that would give me cotangent squared theta plus 1 equals cosecant squared theta. And hence I would have yet another identity that I could use as I see fit. Fair enough? Okay. So what advantage do I have with these particular equations? Well, sometimes we're going to be asked for, and we have been asked, but we've kind of gone about it in a different way. But if I were to ask you, if I told you that, let's just say that for argument's sake that the tangent of theta was, let's say, 5/6. Okay, that right there is not a nice value. True? It's not a unit circle value. My question would be then, could we find the sine of theta, let's say for argument's sake? If I knew the tangent of theta, could I find the sine of theta? Okay. Obviously I can find the angle because I can do the tangent inverse of that. I would get an angle that's not very nice, of course, though. Okay. Okay, but could I find the sine of theta? Okay, essentially it would be nice if it were a nice answer, an exact answer like 5/6 is. Okay, could I find that? Well, ultimately, if we know that, tangent of theta, one thing that you have to caution you on here is that some people in the past have said, oh, if tangent theta is 5/6, then wouldn't sine be 5 and cosine be 6? Oh, why not? Okay, if I wrote that sentence down, okay, how would you know that that can't be true? It can't be bigger than 1. The range of the sine function is -1 to 1. Can the sine ever be 5? No, again, think of the bigger picture. If you were to graph sine and graph 5, would they ever meet? No. So that's definitely not true. Okay, so the question is then, how do I find other trig values then if I know one trig value? Well, couldn't I plug it into this and find secant? And if I knew secant, okay, wouldn't I also know cosine? And if I knew cosine, okay, couldn't I use that to find sine? True? So really, if I know one, shouldn't I be able to use one or more of these sentences to find all of them? Sure. So let's do that. So if I do 1 plus, and here's where another part where people usually mess this up. If I'm going to use this equation right here, 1 plus tangent squared equals secant squared, here's where we have to be careful, is that the tangent of theta is equal to 5/6. So that means when we put it into the equation, it's going to be 5/6 squared. Okay? So one thing that people generally do is they'll take and they'll put 5/6 in for theta. But remember, that doesn't say theta equals 5/6. It says tangent theta equals 5/6. Fair enough? So don't make the mistake of doing this, of writing 1 plus tangent squared of 5/6. Okay? That's usually how people mess it up, is they put it in for theta instead of for tangent theta. Okay? The entire tangent theta is getting replaced with that value. Fair enough? Okay. So do not do this. Okay? Instead, do this. And then I need over here, that equals secant squared. Okay. And so if I do the math on that, I'm going to get 1 plus over here is going to be 25 over 36. Okay. If I make the 1 into a 36 over 36, 36 and 25 is going to make 61. So therefore there would be my secant squared theta. Okay. Keep in mind that's the secant squared, so to get the secant I'm going to need to take the square root of both sides. So I'm going to end up with the square root of 61 over 6 equals secant theta. True? Alright. And of course if this is a number here that can be reduced at all in the radical, we'd want to do that as well and reduce any fractions that we have outside as well if it turns out that way. And once again, I'm not going to go through the process here, but at this point you'd be able to figure out the cosine because you just flip it. And if you knew the cosine, then couldn't you go back to this one and do the same process and solve for the sine that we need ultimately? Okay, good. Okay, questions so far? Okay.
What about the a squared plus b squared equals c squared?
That's ultimately how we got this first one, because we're doing, this is our a and our b, if you will. So this is our, let's say, our a squared plus b squared, and c squared would be 1 squared. Right? So all this is because of the Pythagorean theorem, essentially. That's me. Okay. Yeah. So all these identities rely on the fact that we have a right triangle here, and that the Pythagorean identity is true, or the Pythagorean theorem is true, I should say. Okay. Anything else so far? All right. Did that one. These identities here are just ultimately what we've kind of already talked about here. I will put it up here just so you can see it. Anytime we have a right triangle, legs x and y, hypotenuse r, they called it. Okay, we know that the sine of a, okay, is going to be, of course, the opposite over the hypotenuse. These just come from our SOHCAHTOA information. One thing to note here too is that if we have sine of a, okay, notice that that's the same value as the cosine of b, isn't it? Okay. So if I had b, it would be the adjacent for that particular angle over the hypotenuse, it would still be y over r. Okay, so we know how to find all those in the trigonometric ratios. That's nothing new for us. We do have what we call cofunction identities. Okay. And these are essentially a result of the fact that these graphs are shifts of each other. Okay, we know that sine and cosine are just shifts of each other. You remember, if I look at sine here, and I have pi over 2 minus theta, normally it's in the form of pi plus or minus something. But we know in general that if there's something being added or subtracted to our theta, okay, it's going to create a shift. Okay? And so with that said, these cofunction identities come from the idea of our graphs being shifted. Okay? And then we also have what we call even and odd identities. Okay, we know that sine and tangent, cosecant and cotangent are all odd functions. Okay, so these two are odd. So therefore, sine of the opposite of x, or cosecant of the opposite of x, will always produce the opposite of sine x, opposite of cosecant x. These two are also odd. Okay, we know that these two, cosine and secant, are both even. So therefore, the cosine of the opposite of x is going to equal the same thing as cosine x equals. Okay. If we were to look at the graphs of these functions, okay, we would recognize that these two are symmetric over the y-axis, okay, and hence evenness, and this property holds. And these four, if we look at the graphs, we know they're going to be symmetric over the origin, and therefore we would have an odd function, okay, which again indicates anytime we have the cosine, or the cotangent or tangent, sine or cosecant of a negative of an angle, that equals the opposite of what the angle equals. Okay. All right.